Hi, and welcome back to my series of videos for Physical Chemistry 1. In the last video, we looked at the details of the motion of molecules in a gas, and we found we could describe it in pretty fine detail using properties like the collision frequency and the mean free path. But actually, that was just one type of motion that molecules undergo, and the energy of a molecule is only partially a result of that type of motion. The kind of motion we've been talking about so far is called translational motion. That's the motion that an object makes as it travels through space in a straight line. By now, we've looked at the translational motion of molecules pretty thoroughly, but that's not the only kind of motion that molecules perform. In previous courses, you probably talked about infrared spectroscopy, and you probably learned that an IR spectrum gives us information about the vibrations that the atoms in a molecule perform. We'll talk a lot more about molecular vibrations and infrared spectra in the Physical Chemistry 2 course, which I hope you'll take next semester. For now, it's enough to be aware that the atoms in a molecule vibrate. The simplest type of vibration is one in which two atoms that are bonded together move toward and away from each other. The atoms move like they're connected by a spring. As a result, the bond between the atoms gets shorter and longer. As you can see, this is another form of motion. It's just internal motion within a molecule, not motion of the molecule relative to the room. In addition, molecules can experience rotation around an axis. This can happen around any axis, and if we wish, we can determine the orientation of that axis in the XYZ coordinate system. Like vibrations, rotations are a form of internal motion. As we'll see soon, translational motion through the room, vibrational motion, and rotational motion all contribute a different amount to the overall energy of a molecule. But there's more. In addition to these three forms of motion, a lot of a molecule's energy comes from the electrons. As you learned in general chemistry, electrons can be in different energy levels, and each of these has a different potential energy that contributes to the overall energy of the molecule. So, overall, the energy of a molecule is a combination of contributions from the electronic energy, the vibrational energy, the rotational energy, and the translational energy. One thing we'll want to get a clear picture of is how these different energies are related to each other. To start with, let's think about the lowest energy state of our molecule. As you might remember, the electronic energy is lowest when the electron is in the n=1 state. That's called the ground state, and as you might guess, the molecule can also be in the lowest vibrational and rotational energy levels too, which are called the ground state vibrational or rotational energy levels. Just like the electronic energy level has the symbol N, the vibrational energy level has the symbol V, and the rotational level has the symbol J. The ground states of these forms of energy happen when n=1, V=0, and J=0. As you know from previous classes, electrons can be excited to higher energy levels, and these have numbers n=2, 3, 4, and so on. The energy of each level is higher than the one before, but the energy increase is a little less every time we increase n, so the energies get closer and closer together as we go to higher energy levels. But what about other forms of energy? It turns out that each of the electronic energy levels has a set of vibrational energy levels associated with it. For example, if our molecule is in the ground state electronic level, we can add a little energy and excite the vibration into a higher state. We're not adding enough energy to send the electron into the n=2 level. It's a much lower energy than that. And that allows us to get an excited vibrational energy without leaving the ground state electronic energy. Just like the electronic energy levels, the vibrational levels get closer and closer together as we raise the energy. Each electronic energy level has its own set of vibrational levels, so if we look at both types of energy levels, the diagram starts to look fairly complicated. And we haven't even talked about the rotational levels yet. Each of the vibrational levels has its own set of rotational energy levels. Just like the electronic and vibrational levels, these get closer together as we raise the energy. So when we combine the electronic, vibrational, and rotational levels, this diagram looks very messy. But let's look at what this diagram is actually telling us. The electronic energy levels are spaced apart by a fairly large energy, and for that reason, it takes a photon with a lot of energy to raise an electron from one electronic level to another. This often requires photons with a visible or ultraviolet wavelength. For that reason, we use a UV-Vis spectrometer to detect transitions between the electronic energy levels of a molecule. Meanwhile, the vibrational energy levels are spaced more closely together, so it doesn't take as much energy to cause transitions between the vibrational levels. If you check the electromagnetic spectrum, you can see that photons in the infrared region have lower energy than visible photons. That's why infrared spectrometers are used to detect vibrations in molecules. As you might guess, we use photons with even lower energies to detect transitions between the rotational energy levels. The photons we use are in the microwave region. So, rotations, vibrations, and electronic transitions are each detected using a different wavelength region. You might have noticed that we didn't mention the translational energy levels. That's because they're extremely close together in energy. So close that they seem as though there is no separation between them. We don't usually talk about translational energy levels because translational energy can have almost any value. Notice that the electronic energy levels don't involve motion of any kind. The electronic energy is purely potential energy. On the other hand, the translational, rotational, and vibrational energy levels all do involve forms of motion. And those forms of motion are called degrees of freedom. To understand degrees of freedom, it's easiest to start by thinking about the energy that arises from each of the three types of molecular motion: translations, rotations, and vibrations. Let's look at translational energy first. It turns out that the average translational energy in one dimension is 1/2 times kb times t. Kb here is a constant called the Boltzmann constant, and it's just equal to R, the gas law constant, divided by Avogadro's number. Kb is a number that comes up in a number of different equations in chemistry and physics, so it's worth remembering. Meanwhile, rotations have a similar energy. It turns out that rotation around an axis has a value of 1/2 kb times t, just like the translational energy in one dimension. What about vibrational energy? Each vibration contributes twice as much energy to the molecule as a rotation does. So each vibration contributes kb times t. So now we know how much energy each translation, rotation, and vibration contributes to the molecule. To get the total energy a molecule has due to various types of motion, we multiply each energy contribution by the number of translations, rotations, or vibrations the molecule can experience. Those numbers are what we mean by the degrees of freedom. So, how many translational degrees of freedom are there? It turns out that every molecule can move in the x, y, or z direction, so there are 3 translational degrees of freedom. What about rotational degrees of freedom? It might seem like every molecule would have 3 rotational degrees of freedom because a molecule can rotate around the x, y, or z axes. Most molecules do indeed have 3 rotational degrees of freedom, but that's actually not true for all molecules. For example, consider a acetylene molecule. Suppose we define the axes so that the z-axis is oriented along the bond. Now imagine what rotation around each of the axes would look like. Rotation around the x-axis makes the molecule twirl like a propeller, and rotation around the y-axis does the same. However, rotation around the z-axis doesn't have any detectable effect on the molecule. Since the molecule is symmetric around the z-axis, rotating around that axis has no effect on the molecule or its energy. So, for a linear molecule, there are just 2 rotational degrees of freedom, not 3. That means that for a nonlinear molecule, there are 3 translational degrees of freedom and also 3 rotational degrees. For linear molecules, there are 3 translational degrees of freedom, but only 2 rotational. Now imagine what happens if we just have one atom, like a helium atom. Single atoms are nearly spherical, so for a helium atom, rotating around the x, y, or z axis has no effect on the atom. That means there are no rotational degrees of freedom for a single atom. However, there are still 3 translational degrees of freedom, because the atom can noticeably move in any of the 3 dimensions. What about vibrational degrees of freedom? Well, there are no vibrational degrees of freedom for a single atom because there aren't any bonds that could vibrate. For linear molecules, it turns out that there are 3n minus 5 possible vibrations, and for nonlinear molecules, there are 3n minus 6 vibrations, where n is the number of atoms in the molecule. So, for example, carbonyl sulfide is a linear molecule made of 3 atoms. Therefore, it can undergo 3n minus 5 vibrations, for a total of 4 altogether. On the other hand, the molecule methylamine is a nonlinear molecule made of 7 atoms. Since it's nonlinear, it can undergo 3n minus 6 vibrations, for a total of 15. So, here's a summary of the number of degrees of freedom for translations, rotations, and vibrations for different kinds of atoms and molecules. If we combine this with the energy for each type of motion, we get this equation for the overall energy of the molecule due to different forms of motion. We can simplify the equation a bit by factoring out 1/2 kb times t, which gives us this equation. Notice that we've been using the Greek letter epsilon for the energy instead of the letter E. This is because we're calculating the energy for just one molecule. Of course, ordinarily we want the energy of a much larger sample, something that we could see with our eyes. To get that, we'll just multiply this equation by the number of molecules, which we'll call capital N. We can simplify this equation a bit. Recall that Kb, the Boltzmann constant, is equal to R divided by Avogadro's number. But N divided by Avogadro's number is just equal to the number of moles, which is little n. So that gives us this for our equation for the energy of a sample of molecules based on the degrees of freedom in the molecules. It's most accurate for samples that behave like ideal gases. This equation is a very easy way to determine the energy due to the motions of molecules in a sample, and it's known as the Equipartition Principle. One of the most useful things we can do with it is determine the energy that would be needed to heat a sample. Let's try it. Suppose we have 3 samples of gas, a mole of helium, a mole of acetylene, and a mole of water. We heat each sample from 400 Kelvin to 500 Kelvin. How much energy would be needed to heat each of the 3 samples? To answer this question, we'll use the Equipartition Principle to calculate the energy of each sample at 400 Kelvin and at 500 Kelvin. Let's start with the sample of helium. We have 1 mole. R is 8.314 joules per Kelvin mole, and the temperature is 400 Kelvin at the start. Because this is a single atom, there are 3 translational degrees of freedom, 0 rotational degrees of freedom, and 0 vibrational degrees of freedom. That gives us 4,988.4 joules. When we do this calculation over again using the final temperature of 500 Kelvin, we get 6,235.5 joules. So that's a difference of 1,247.1 joules. So that's the energy that would be needed to heat the mole of helium from 400 to 500 Kelvin. Now let's try it again for acetylene. Once again, we have 1 mole, R is 8.314 joules per Kelvin mole, and the temperature is 400 Kelvin at the start and 500 Kelvin at the end. Acetylene is a linear molecule made up of 4 atoms. So, there are 3 translational degrees of freedom, 2 rotational degrees of freedom, and 7 vibrational degrees of freedom. That gives us 31,593.2 joules at 400 Kelvin and 39,491.5 joules at 500 Kelvin. That's a difference of 7,898.3 joules for acetylene. Finally, let's try it for water. The number of moles and the temperatures are still the same. Water is a nonlinear molecule with 3 atoms. So, there are 3 translational degrees of freedom, 3 rotational degrees of freedom, and 3 vibrational degrees of freedom. That gives us 19,953.6 joules at 400 Kelvin and 24,942 joules at 500 Kelvin. That's a difference of 4,988.4 joules for water. So, the equipartition principle is a helpful way of determining the energy needed to change the temperature of a sample of gas. And there's one more especially useful application of the equipartition principle. The constant volume heat capacity of a substance is defined as the rate at which the energy of a sample changes with temperature. In other words, it's the derivative of the energy with respect to temperature. According to the equipartition principle, the energy is equal to this. The number of moles, R, and the degrees of freedom are all constants, so the derivative of the energy with respect to temperature is equal to this. So, we can use this equation to determine the constant volume heat capacity of any gas as long as it behaves like an ideal gas. So, for instance, let's determine the heat capacities of a mole of helium, a mole of acetylene, and a mole of water. We already determined the degrees of freedom for each of these gases a little earlier in the video, so we'll plug those values into the equations. That gives us a heat capacity of 12.471 joules per Kelvin for helium, 78.983 joules per Kelvin for acetylene, and 49.884 joules per Kelvin for water. Well, that's enough new material for now. In the next video, we'll start our discussion of chemical thermodynamics. It'll be the main topic for the remainder of the course, and it's a subject that underlies a lot of the theory of chemical reactions. I hope you'll join me for that. But until then, have a good week.